Hello, everyone. My name is Mohammed. I am part of the Essential team. We are building the first declarative blockchain, and this is a workshop on how to build declarative applications using our smart contract language Pint and deploy it on the Essential chain and test it out. Now, as a prerequisite for this workshop, you should look at the Getting Started guide that you can find on our docs website, docs.essential.builders. The Getting Started guide will walk you through the installation process, how to get into or install and enter a Nix shell. And the Nix shell will have all the tools you need to start building. And the guide will also walk you through how to build a simple project, particularly a counter example, which basically has a counter in storage that increments by one every time you submit a solution to it. So I highly suggest you walk through that and make sure you complete that guide before watching this video. I think walking through a more complex example in this video is a little bit more useful for you. So by now you should have, and I have it here, this is a Nix shell, which I've entered, and as explained in the Getting Started guide, you have to install Nix and enter a Nix developer shell. All the commands are in the guide. Once you have that, you'll find that you have tools like Pint. So if you do which Pint, it will link you to the Pint tool, which allows you to build Pint contracts. So what we're going to look at today is a token example. A token is a little bit more complicated than the counter. It has slightly more interesting things going on, and then particularly authentication and some other things. So what I'll start with is I need to first create a directory called token, and then I'm going to use the Pint tool to create a new project called token under token slash contract. So I'll make the contract under a directory under this directory. So if I go here, I can now see that I have a toml file which describes of my project, and I also have a source directory in which I have something in here. I have a basic counter example which I'm just going to get rid of, and then I'm going to start working through the token example. So let's think through what the token needs. The first thing that token requires is some sort of a map between addresses or accounts and values. So for that, we need a storage block. A storage block looks like a storage followed by a list of variables in here. And for the token specifically, we need, among a bunch of things, we need a balances map. And the way we write a map in Pint is via the syntax, which says I'm mapping B256 to integers. So B256 represents addresses, 256-bit addresses to integers, which are my balances. I could put other stuff here, like the total supply and maybe a ticker for the token and all that kind of stuff. But I'm not going to worry about that just yet. Now, each Pint contract has a list of predicates. So a predicate is basically a collection of constraints. Again, we're talking about a declarative language. So we're not actually describing how operations work or how state gets updated. We're just describing what we want the state to be or what we want the future state to be. And for that, we just list a sequence of constraints that constrain my state. Let's start with a predicate called mint. This is how we declare a predicate. It's just a predicate keyword followed by the name of the predicate. And we're just going to start by adding a list of decision variables. Now, a decision variable is basically a local variable that every solution has to set. Think of it as a parameter for the predicate. It is not a state variable. It doesn't live in storage. It's just a temporary thing that the solution sets, and then it basically parameterizes the predicate in some way. So how do we want to parameterize the mint predicate? We want a variable called 2 of type B56. Var is the keyword here to declare a decision variable. And then we need an amount. So the idea with a mint predicate is to create a certain amount of tokens called amount and send that amount to an address called 2, which is why the type of 2 is B256. Now, I don't initialize these things. These are things that are set in the solution, which is why they're just variables. Now, let's think through some of the constraints. The first constraint, I could put constraints like I need the amount to be greater or equal to 0. This makes sense. Like if someone sets a negative amount here, it kind of doesn't make a lot of sense. I'm not going to mint a negative amount of tokens. So this is kind of a safety constraint. It's something that if this is a constraint on the parameters. So if this is not set, then if this constraint is not satisfied, then the predicate will fail, and the solution will not proceed, will not be accepted. Now, what I need to do is to increase the balance of 2 by amount, assuming all the conditions are satisfied. So how do I do that? The first thing I need to do is to access the location in storage where the balance of this particular address is stored. So how do I do that? I need to create something called a state variable. And this is a variable that starts with the word keyword state. And I'm going to call that balance. And I'm going to initialize that to storage colon balances of 2. So this is saying access this storage map with the key 2, right? So I'm just going to, because this is a map from addresses to ints, I can pass in 2 here in between brackets. And what I'm saying here, I'm basically accessing this particular storage slot. There is no actual reading happening. This all happens at solve or validation time. This is just a description of what I want balances to, or this balance variable to be. So now that I have the balance, I can say, okay, I need the balance to increase by amount, right? This is what the mint does, the mint predicate does. It basically creates some amount of tokens and then sends them to balance, or to not send them to this particular address. And the way I do that is via this syntax that says, okay, so I need my balance prime. Balance prime is the new balance. And I'm going to set that to balance plus amount. So this is saying effectively increase the amount of balance, the current balance by amount. So the new balance is going to be the old balance plus amount. And notice that this is a Boolean expression. It just says that the future balance is the same as the current balance plus amount. Now, what other constraints do I need? I need a constraint like this. And I'll say what minter is. Minter is effectively a specific address that I'm minting to. Now, it's probably the case that only some particular owner is allowed to mint stuff to themselves, mint tokens to themselves. And so I'd like to restrict the person or the account receiving the tokens to be a particular address called minter. Now, this is a const minter, which I can declare at global scope here. I can set the type for it if I want. It's optional. And I'm going to set the value to, I'm going to copy it from here. And I will explain where this number comes from. That's going to come in handy later on when we look at the tests. So we've made sure that the account receiving the tokens is actually minter, which is good. Let's see, what else are we missing? We're missing authentication. So we're missing the fact that we want to make sure that the account that's actually making, or the account that the solver is proposing a solution on their behalf is actually the minter, right? So this is our version of authentication. Now, authentication in Essential, you kind of have to do it manually, and I'll show how in a second. So for that, I need to start with a signature. So a signature has to be provided by the solver on behalf of on behalf of the user or the account that's requesting the mint. Now a signature, this is a type that I'm going to create here. I'm going to create a type alias for, and that's what a signature looks like. It's a tuple that contains, it's effectively 9 words. Note that in the Essential VM, every integer is a single word, and every B256 is clearly is 4 words because integers are 64 bits. So every word in the Essential VM is 64 bits. Now a signature is just a sequence of words like this, and I am going to call a macro here, which I will declare later. Validate signature, and I'm going to validate a signature. You need 3 things. You need the data that you've signed on. You need the address, and you need the signature itself. So I'm just going to do that here. I'm going to pass in the signature. I'm going to pass in the 2, which is the account, and I'm going to pass in the data that I'm going to be signing over. So what this is saying is I'm passing in the signature, the 2, and then a tuple that contains the data that I'm going to be signing over, which is the rest of the decision variables. Now, how does this? I'm going to copy this particular macro here because you're probably going to have to do the same. And this macro takes in 3 things and returns this expression. So this expression is a Boolean, naturally. It basically says sign over the data, hash the data, and then recover the public address given the hash of the data and the signature. And then you hope that the return public address has a hash that is the same as the key that I'd like to validate. So in this case, what we're saying is when we call the macro with these things, we're saying we're passing in the signature, the 2, and the 2 comma amount. So we're hashing the data. Then we're saying recover the public address given the hash of this data and the signature, and then make sure that the resulting public address, if you hash that because the public address has more fields in it, you hash that, you get back a B256, and the result of that must match this particular basically 2 here. So now we validated the signature, and I think we're ready. If we want to basically compile this, so we're going, let's see where we are. Okay, we're going to go to the contract project, or the token project, in the next shell that we have. And then we're going to write find build. So find build, and this is going to build my contract. And it passes fine. It gives me, the output here contains the address of the contract as well as the address of the predicate. These are the content hashes of the contract and the predicate respectively. These are useful for deployment or for referring to specific predicates or contracts from other external contexts. So now I have what I need. The main predicate has been written, and I have everything I need. Now, there's one little caveat here with what I wrote. You may be wondering what happens if balance here has not been set before. So what does that mean? Let's say this particular address has never received any tokens before, which means it has no entry in this map. Now, you probably have seen that in the contract or in the counter contract. And the way I prevent from anything bad happening is by first checking if balance has been set before or not. And the way I do that is by checking that balance is nil or not. So what I do is say if balance equals nil, otherwise do something else. So if balance is not nil, what I'm going to do is I'm just going to do this. Basically, I'm going to increment it. And if balance is nil, I'm just going to set it to amount, because I'm going to assume that the previous value was in fact 0. So it just hasn't been set in the map before. So this particular address or this particular account has no tokens. So the new balance is going to be just amount. Let's build again. Let me see if I'm forgetting anything. I don't believe I am. In fact, there's one thing that I will, so mutability. This is something that you've probably also seen in the counter example. I need to declare this particular storage access as mutable. And the mute keyword comes on this side, which I know is a little bit weird, but in the future, we're going to be able to pass in arbitrary storage or storage accesses here, which means you can set each particular one as mute. So mutability applies to the storage access, which is effectively saying the key where this thing is stored is mutable and not the state variable itself. So this is saying may allow the key where this particular expression or this particular storage value is stored, allow this particular key to be changed in this predicate. If I don't have mute here, then the VM will panic because it will see that I'm trying to modify a key in this matter, where the solution is going to try to propose a value for balance, but in fact, this particular key is not allowed to change because everything is non-mutable by default. So I need to set this particular key to mutable. This is a very, very important point because if I don't have if things are allowed to be changed by default, then solvers could submit any solutions and modify any storage slots they feel like it. They could improve their own balances. They could improve anyone's balance. They could decrease anyone's balance, and nothing is there to prevent them. So making sure that every key is immutable by default, and then you have to opt into mutability within the predicate that you're trying to solve is important. It's kind of a security concern. So this is the main function. It's pretty nice. Now I'm going to build kind of a simple application around this contract and hopefully test it out. So I'm going to come here, get into the token directory, and I'm going to create a new Rust project. Cargo new library counter app, or the token app, I should say. Gonna add it in here. And the first thing I'm going to do, I'm going to have to add a bunch of dependencies. Now we'll copy those, and you can do the same. I will link to this particular you'll have access to all of these things via GitHub link later. So this is the toml file where all the dependencies exist. And then I should be able to go back here and go to the token app and then at least build. So if I build this, it will take a little bit of time. So while we download all the dependencies, I'm going back here and I'm going to just erase everything in the lib file, and I'm going to add my own stuff. So let's see, what do I need here? Again, I will copy a bunch of things. So we haven't written the transfer function, so I'm going to comment this out. And so let me see. All right, so this works fine. So what do we have here? So I'm building basically a periphery application, or a front end, if you will, that is able to interact with the contract. So what does that mean? So I'm going to start with a struct called app, which is just my application that I'm going to be able to create instances of in the tests. And this app takes in a client, a wallet, and a bunch of addresses. These addresses are basically the addresses of the token contract, the contract itself, then the addresses of all the predicates in the token. As I said before, these are basically the content hashes of the corresponding code. One thing I'll need, and I didn't talk about the ABI yet, but the ABI is a file that gets generated by the bind build tool. Once you build a contract, you will automatically get an ABI file, which I should probably show here. Token contract, and to find that file, you look in the out directory of the contract that the contract project. If you look here, it's kind of self-explanatory. It basically lists all your predicates and lists your storage. So this is kind of a JSON representation of your storage block. It says, oh, I have balances here, which is of type map from to these types. And then I have my predicates. I have a single predicate so far called mint. It has some vars. Each var has a name and a type, and so on. So it's pretty self-explanatory. So these are all the things that a solver needs to know about to be able to set a solution, or to be able to reason about a solution. Same with validators. And the way we would use this file is via an ABI gen tool. So it's a macro that you can access via the bind ABI crate, and it takes in ABI, basically a path to your ABI file, which is in this case lives in my contract directory, contract/house/debug. and the contract itself. Now, if you look in here, you'll find another file in the output/debug directory, which will not make a lot of sense to you, but this is just the JSON representation of the bytecode that represents the contract. So you don't need to read this, but obviously tools are able to parse it. Now, what this does is it will allow you to access all the types that are created in your contract and allows you to basically read and set storage variables or storage state mutations, as I will show later. Now, I need to start implementing functions on this application. I'm going to start with a new function, which is pretty straightforward. It just sets the client. The new function that takes in a server address. That's all boilerplate code that I suggest you mostly copy. And then I need a min function. Now, this min function effectively, because when the min function typically in imperative ecosystems, you typically make calls to the contract to test them out. For us, there are no, or in essential, there are no calls. There are no contract calls. All you do is propose solutions. And to propose a solution for the min predicate, what you do is you basically have to craft a solution down here, which I will explain in a bit. You craft the solution and you just submit it, and then you hope for the best. And what that means is you submit the solution, and you hope it gets picked up by a solver. And when that happens, if the solution gets accepted by the validators, then the state updates proposed in the solution will in fact go through, or will in fact be committed. So let's look at the min function briefly. We need to craft a solution, as I said earlier. So a solution is basically an object that looks like this. It has a bunch of solution data. So it's a list of solution data objects. And each solution data solves one predicate. So in our case, we only need to solve a single predicate. But in other cases, you may want to solve one predicate from each contract or multiple predicates simultaneously from many different contracts or within the same contract. It doesn't really matter. And this is important for applications that need to interact with multiple contracts. So if you're writing an exchange application, for example, then you probably need to do that, because then you have to interact with your exchange contract as well as the token contract. So this is something you might want to look at or try during the hackathon. So what is a solution data? It basically starts with predicate to solve, which says, this is the predicate that I'm trying to solve. It's basically the address of the predicate, which is what I got here, by the way. If you go back to contract and you do build, this is the token, or this is the mint address. It's basically a combination of the token address or the contract address and the predicate address. The decision variables, I need to set the decision variables. I go back to my token or my contract. If I go back here, I'm gonna open it in this window. I have 3 decision variables: to, amount, and signature, right? So because I am using the API, because I've made this macro call here, I have access to an object called mint : vars. Now, mint is the name of the predicate from the API generated code, and vars lives within this module, and vars has all my values. So vars expects 3 fields: the to, the amount, and the signature. So the to is basically the address, which in fact matches this one here. And the way I've done this is by calling this get hashed key, which is defined later, and basically accesses the wallet. So the wallet which I'm not going to go through too much here. You can study that on your own. But effectively, it's saying, get me the public key for this particular account name. The wallet has a list of accounts, a map between the account names as strings and their public keys. And I'm going to take that public key and I'm going to get the hash of it. So that's what 2 is. So I'm going to get back an array. So if you look at what the type of this is, it's in fact, I believe it's an array of 4 I-64s. Yes, because that's what the B256 is. It's 4 words, and every word is I-64. So this is the first decision variables. I'm going to set 2 here. I'm going to set the 2 to this particular key, which in this case is the minter. The amount is what I'm passing as a parameter for this function. That's how much I want to mint. So when I'm testing this function, I can set this whatever you want. And the signature is I just need to sign over the data. So what do I need to sign over? As I said before, sign data is basically another function that I've defined later. And it basically uses a sign words method from the wallet. And we're just going to encode it in a very specific way. And the way we do this is because the signature, if you remember here, the signature type is basically B256, B256, and an integer. So I need to encode the signature as such. So it's basically, that's an array of 4 integers, so a B256, and then that be another B256, and then an integer. So that's how I encoded the signature. Now I have the signature, I can just pass it as a decision variable as well. Now that I've set all the decision variables, I need to set the transient data, which I'm not going to talk about too much here. You can look at some of the more complex examples in the integration repo or the sample app repo. And then finally, the state mutations. This is where the magic happens. State mutations are basically, we say, storage colon mutations. All of these are available as part of the ABI gen that I've done earlier. And I'm going to take the balances here, the balances map. Notice that this is available here, the same name that I used in the contract. And it says, I'd like to map to this new value. So I'm mapping I'm setting effectively the balance of 2, the key that will receive the minted tokens, to current balance plus amount, right? Which is kind of clear. Now that's what a solution is, right? It's meant to give me the new balance, or it's propose a particular state update that when I check it later in the contract, it's actually correct. Now current balance, I need to get that. So how do I get current balance? I need to query the current state. And the way I do that is I show later in this, it's a helper function that gets me the balance of a particular account. So yeah, you get, I just happened to give it account names as strings, and so we get the key out of that first, and then we query the state. So to query the state, we need to get the location where this particular value is stored, or where the balance of this particular account is stored. And the way I do this is using the keys interface, similar to mutations above. Keys is very similar here. It says, get me the keys, get me a list of keys, and the first of them has to be the place where the balance of account key lives. So I'm going to get a vector that contains, in this case, just a single key. So I'm going to use it here. And that's the query state function or method on the client, allows me to get back a value. And then I have a match statement here that says, if you don't get back anything, just set it to 0, which is kind of reasonable. It says, if nothing has been, if this particular key has not been set before, then what I get back is 0. So no balance at all. So yeah, that's pretty much it. Now that I have the current balance, I'm going to add amount to it. I'm going to propose that the new state value is in fact current balance plus amount. And then I have my solution, which is, as I said, it's a vector of solution data. And in this case, it's just a single solution data that I have to deal with. And finally, I'm just going to submit the solution. Pretty straightforward. That's pretty much it. Let's see how we test this. So I'm going to go back to the token app, and I'm going to create a test directory, and I'm going to add a token.rs test. I'm going to paste some more stuff here. I'm testing the mint, right? So again, all of this is just boilerplate code. Won't go too much into it. So I'm going to remove everything to do with transfer because we really haven't looked at that. See if that's going to work. All right. So test mint, we're going to have a bunch of boilerplate code here. We're basically setting up wallets and setting up accounts for each party. In this case, we're only going to need Alice, which is the person who is, or the account that is allowed to mint. And so the first thing we'll do, the first thing we'll do is set all the addresses, which I'm basically setting those using the content address method, which, as I said, the addresses of predicates and contracts are the content hashes of the corresponding bytecode. So I'm just doing that manually here. I could pick them up from the command line if I want, kind of the same idea. And then I'm going to deploy the contract, right? So sign and deploy. We take the token contract object, and I'm just going to deploy it. And now I'm ready to do whatever I want. So I'm going to create an instance of the application with the server address, and then I'm going to start doing things. So the first thing I'm going to do is query the balance of Alice. So since nothing has happened so far, the balance should be 0. Remember that when you query the balance, in fact, I'm calling this function here. So this token.balance is in fact this function which queries the balance from the blockchain. And if the balance does not exist, I'm just going to return a 0. So it's exactly what happens here. Then I'm going to submit a solution. I'm going to submit a solution for the mint function. And the way I do this is by calling the mint method here, which, remember, does not actually make any contract calls because that doesn't make sense for us in a declarative context. I'm just proposing it. So the mint function is actually just proposes a solution. And the solution it's going to propose is to mint this many tokens, 100,000 tokens, to Alice. Right? So I'm just going to go back here. When I call this, an amount will come in here. It's going to read the previous balance. It's going to add amount to it. And it's going to propose that the new value or the new balance of for Alice is, in fact, 0 plus amount. So I can now, once I do this, I'm going to wait a little bit, and then I'm going to check the new balance. So I'm going to check the balance here, and I'm going to make sure that, in fact, the new balance is the mint amount, right? It's just because Alice had nothing before. And I'm going to repeat the same thing. This time I'm going to mint 200,000 tokens. I'm going to do the same, call mint. I'm going to wait a little bit. I'm going to check the current balance. I'm going to make sure that the current balance is actually the first amount plus the second amount. So the current balance is now 100,000 plus 200,000, which should make sense. And that's it. That's it for my test. Now, what's really happening here? Just some some conceptual things to keep in mind. When we call submit solution, and then we wait, and then this particular solution gets validated. Because I have predicate to solve set to a particular predicate, which does match this particular predicate here, what happens is this solution gets propagated, and basically the validator or the essential VM will plug everything in the solution and make sure that every constraint here is satisfied. So we're going to make sure that the amount that I set here satisfies this constraint. Otherwise, the VM will return, well, the predicate will fail, the VM will panic, and the solution will not be accepted. And I'm going to check that the new balance is the old balance plus amount. I'm going to check that the account that I'm minting to is Minter, which matches the address for this for the account owned by Alice. And I'm going to validate the signature. And so the signature that I set here using signed data must match or must satisfy this constraint, which is really important. So all of that's happening once I submit a solution and the solution gets validated. So the validation process, which happens during the sleep time that I have here, when I submit a solution and then I wait. During that period, the solution is going to get validated, and when it gets validated and all the constraints are satisfied, then the state is going to be updated. So yeah, that's pretty much it. This is how I would write a mint predicate, and how I would write a periphery or a front end for it, and I test it out. You could try the same. You could try to implement a transfer function and do the same. Should be kind of a natural extension to this. And what I recommend is you look at the repository, which it's kind of where is it? So this repository over here will contain everything I talked about, including the counter example. And most importantly, you should check out the sample apps repo, which I'm linking to here. If you go to sample applications, this has full examples, NFT counter token, that are in fact doing more things. So there's a few things that I'm missing in the token example. There's the nonce that you have to deal with, and there's more complex code that handles authentication for accounts that are not EOAs. So validating signatures here is somewhat easy because we're dealing with accounts, wallets, and we're not dealing with other contracts. But to make the token contract more interesting, you need to be able to handle signatures or handle authentication for accounts that are other contracts or other predicates. And this repo, this token example shows you how to do this. It's a bit more involved, and I suggest that you study it well. So yeah, and really everything, this repo has more links. There's the quick start guide, which I talked about earlier, the reference for the Pint language, and the specs for the protocol itself, if you need that. And yeah, that's pretty much it. Just keep in mind that all of this stuff is still work in progress. There are certain limitations to the language so far. So for example, we don't have dynamic arrays, we don't have dynamic vectors in storage. We don't have a way to loop dynamically over things. Those are not really required for many applications. I believe we should be able to experiment with many different things without those things. But yeah, just something to keep in mind. And yeah, and I think I will end it here. Hopefully this is kind of somewhat useful. and will help you get going with building whichever application you have in mind. Lots of things you could look at, even just looking at a different implementation of the token contract, and looking at how you can improve authentication, how you can think about making it more modular or making it simpler, looking at name services, looking at escrow contracts or other, DeFi in general, derivative applications, stuff that, anything you can think of, experiment with it. So yeah, it'll be interesting to see what you guys come up with, and good luck.